Lesson 8. Chemical Composition. Objectives. Understand the concept of average mass and explore how counting can be done by weighing. Understand atomic mass and experimental determination. Understand the mole concept and Avogadro's number. Where to convert among moles to mass and number of atoms in a given sample. Understand how to solve problems by asking and answering a series of questions. Understand the definition of molar mass. Learn to convert between moles and mass of a given sample of a chemical compound. Learn to find the mass percent of an element in a given compound. Understand the meaning of empirical formulas of compounds. Learn to calculate the molecular formula of a compound given its empirical formula and molar mass. Introduction. Chemistry allows us to understand matter at the atomic level, but atoms are too small to count one by one. Instead, chemists use mass, averages, and the mole as bridges between the microscopic world of atoms and the macroscopic world we can measure in the laboratory. 1. Average mass and counting by weighing. The idea of average mass. When objects are microscopic, such as atoms and molecules, we cannot count them directly. Instead, we determine the average mass of one particle. Count particles by weighing an extensive collection. Analogy. Just as we count coins by weighing them instead of counting them one by one, chemists count atoms using mass. Key idea: counting by weighing only works if the average mass is known. 2. Atomic mass and its experimental determination. Atomic mass. Atomic mass is the weighted average mass of all naturally occurring isotopes of an element, expressed in atomic mass units, AMU.
Atomic mass igual a sumatorio, se abre paréntesis isotope más veces.
Then the atomic mass of a compound is the sum of the mass of the isotopes times the abundance of each of these isotopes. Why is it an average? Most elements exist as mixture of isotopes. Let's see this concept. Then how can we calculate the average of atomic mass of an element? And we go there.
Why is it an average? Most elements exist as mixtures of isotopes. The atomic mass on the periodic table reflects this natural mixture. Important: atomic mass is not the mass of one atom, it is an average. Calculating atomic mass from isotopes and abundances. Atomic mass is the weighted average of all naturally occurring isotopes of an element, using their fractional abundances. The steps are straightforward and always the same. Method overview.
Okay, in order to convert percentages to fractions, what we do is this. The fraction is the percent divided by 100. Then if you multiply each isotope mass by X fraction, then you can get the contribution of each isotope. And the sum of all the contributions of the different isotopes is what we call atomic mass. For example, we have two isotopes for chlorine. Chlorine 35 and chlorine 37. For chlorine 35, that exactly this is the atomic mass of this isotope. The abundance is 75.77%. And for chlorine 37, that is the atomic mass is 36.96590 atomic mass units. The abundance is 24.23%. As you can see, this isotope chlorine 35, the abundance of it is higher. Then the contribution to the atomic mass average will be higher, and the result will be very close to this atomic mass. Let's let's do this. Then here we have we convert the percent into fraction, dividing by 100, and then you multiply the atomic mass per the abundance fraction, and the same thing for the other one, and then you get two numbers. If you add these two numbers, you will get the average atomic mass in atomic mass units. And this number that you can see here is the one that you can find in the periodic table. Let's see for this element. Oh, for this element, you have here the atomic mass for magnesium 24 and the abundance for magnesium 25 and the abundance and for magnesium 26 and the abundance. After that, you convert percent into fraction, divided by 100, of course. And then you multiply the atomic mass of each isotope per its abundance in form of fraction, and then you sum the products and you get the atomic mass average, or the average of the atomic mass for magnesium. And this number is the one that you will find in the periodic table. Well, here you have two isotopes of one element, isotope A and isotope B, and you have the atomic mass and the abundance. How can you solve this? Well, you convert the percentage into fractions, and then you multiply the atomic mass of each isotope per the fraction that represent the abundance of each, and then you sum the results, and this is the atomic mass or the average of the atomic mass. Well, let's go now to the concept of mole. Let's see.
The mole concept and Avogadro's number. The mole, is the amount of substance that contains 6.022 vis 10 ala 23 particles. This number is called Avogadro's number. What a mole connects. Atoms left-right arrowgrams. Molecules left-right arrowgrams. Ions left-right arrowgrams. One mole always contains the same number of particles, regardless of substance. 4. Converting between moles, mass, and number of particles. Key relationships. Masses IY solo.
Okay, then you can go from mass to moles, and from moles to particles. How can you go from mass to moles? Interesting. Well, if you divide, for example, you have certain mass of one compound. You have certain mass of one compound in grams. So, if you say that one mole, oh, what's going on? I don't know, sorry. If you say that one mole of the same compound of X is certain mass, suppose it is 30 grams, then you can cancel grams with grams, and then you convert mass into moles. But if you want particles, you can say that one mole of any compound is equal to 602 times 10 to the 23 particles. When I say particles, can be atoms, molecules. In this case, we are talking about atoms. Then you cancel up moles with moles, you multiply, you divide, and your answer will be in particles. In this case, atoms of X. Then you can see here how you can go from mass to mole and from moles to particles. How can you go from moles to mole? Let's see. This is another example. For example, you have that 36 grams of water. And you know that 1 mole of water is 18 grams. Then you divide the mass by the molar mass and you get moles. If you want to go from moles to atoms, what you do? You say 1 mole is then divided by this will give you atoms. Then you multiply, here is a mistake, but I'm going to solve it immediately. 0.5 moles, and you multiply here, you divide, you say that 1 mole of this compound is this number of atoms. This is Avogadro's number. 1 mole of any compound is this number of particles. In this case, you're talking about atoms. Then if you use this conversion factor, you can cancel mole with mole, you multiply and you divide and you get what? The number of atoms, that is what you're looking for. Let's continue. Problem solving strategic. Let's go step by step and you will understand it.
Problem solving strategy, asking questions. To solve composition problems, always ask, what is given? What is asked? What conversion factor connects them? Does the answer make sense? Chemistry is logic applied to numbers. 6. Molar mass. Definition. The molar mass of a compound is the mass of 1 mole of that compound, expressed in g/mole. How to calculate. Add the atomic masses of all atoms in the formula. Example. Molar mass of CaCO3. Ca equals 40.08 grams per mole. C equals 12.01 grams per mole. O3 is equal to 3 times 16.00 equals 48.00 grams per mole.
Total igual a 100,9 grams per mol.
Then the atomic mass of this compound is the sum of all these, that will be 109.09 grams per mole. That's the molar mass. And look at this, I'm talking about molar mass of a compound because it's the mass of 1 mole of this compound. Now, how can we convert between moles and mass of a compound? Let's see.
Converting between moles and mass of a compound. Example. What is the mass of 0.75 moles of NaCl? Molar mass of NaCl equals 58.44 grams per mole.
0,75 mol veces 58, 44.
Okay, then, as you can see here, then you multiply 0.75 times 58.44 grams per mole in such a way that you can cancel mole let's see, mole with mole, and then the product of these two numbers will give you in grams. This is the molar mass of sodium, is the number, the mass of 7.75 moles of sodium chloride. Then what is given? 0.75 mole. You multiply them by the molar mass, you cancel mole with mole, and then you get the mass of 0.75 moles of sodium chloride. In this case, you use the molar mass of sodium chloride. How can you calculate this? Is another important thing, the mass percent composition. Well, in this case, the percent of the one element in a compound is the mass of this element divided by the molar mass of all the compound times 100. For example, let's see.
Example. Find the mass percent of oxygen in H2O. Oxygen equals 16.00 G. Molar mass of H2O equals 18.00 G.
4 entre 6 veces 100 igual a 88.
Then you divide the mass of oxygen by the mass of the molecule, and you multiply by 100, and you get that oxygen represents 88.9% in the water molecule. Let's see what is the empirical formula.
Empirical formulas. Definition. The empirical formula shows the simplest whole number ratio of atoms in a compound. Important. It does not show the actual number of atoms. Many compounds share the same empirical formula. Example. Molecular formula, C6H2O6 empirical formula, CH2O. 10. Molecular formula. Definition. The molecular formula shows the actual number of atoms in one molecule. Relationship.
Molecular formula igual a, se abre paréntesis empírico.
Okay, then the molecular formula is equal to the empirical formula times n. If you go here, how can I convert this empirical formula into the corresponding molecular formula? As you can see, it's very easy. If you multiply all these empirical formula by 6, you will get C6H12O6. Because you say 6 times 1 is 6. 6 times 2 is 12. And 6 times 1 is 6. Then this is the molecular formula. Okay? Example, here you have the following exercise. Let me put here.
Empirical formula, CH2 empirical mass equals 14 grams per mole, molar mass equals 28 grams per mole.
N igual a 28 entre 14 igual a.
Then the N, that is the factor, is the molar mass divided by the empirical molar mass. And then you can see that is 2. You have 2 times the empirical formula in the molecular formula. This way you can go from the empirical formula to the molecular formula, knowing the molar mass of each. let's go to this tricky evaluation that I will propose.
Thinking/tricky evaluation questions. Why is atomic mass an average and not a whole number? Why does 1 mole of different substances have different masses? Can two compounds have the same empirical formula but different molecular formulas? Why must the multiplier for molecular formulas always be a whole number? How can mass percent help identify an unknown compound? Key takeaways. Atomic mass is a weighted average. The mole connects atoms to grams. Molar mass links mass and amount. Percent composition reveals elemental makeup. Empirical formulas show ratios. Molecular formulas show reality.
Well, in this lecture, we have seen how we calculate the atomic mass average. How? Well, you have the atomic mass of one of the isotopes. Suppose that the atomic mass of A is 10 and the abundance is 90%. And here you have B, and the atomic mass of B is 12, and the abundance is 10%. Then we convert this percentage into fractions. And then you multiply these fractions by the atomic mass. For example, 10 times 0.9 is 9. And 10 times 12, sorry, 12 point times 0.1 is 1.2. Then you add the contribution of each of the isotopes, and what you get? You get the atomic mass average in grams per mole, and this is what you get in the periodic table. That's why you can see fractions. Don't forget about this. The other important thing that we studied during this lecture is how to calculate the percent of one element in a compound. Suppose that a compound is made of A, that the atomic mass is 16, and B, that the atomic mass is 14. Then you say, what is the percent of A in AB? Then you say, what is the atomic mass of A? 16. And what is the total atomic mass? Is 30. Then you divide and you multiply, of course, by 100. And then you divide 16 times, divided by 30. And the result is 16 divided by 30 times 100 is 53%. Then this is the percent of A. This is the percent of A in the compound. Is, let me write here, 53%. That's the composition of A in the compound AB. But there is something else that I want you to take into account. And it's the procedure to get the the empirical formula of a compound. Suppose that a compound has a certain percent represents, for example, I tell you that a compound, wait a minute, I'm going to give you the example immediately. Okay, here we go. All right, and here we have an example that I want you to observe. For example, then this is the composition. Let me open here a new page. Let me open here a new page. Sorry. Sorry. A page in blank. Okay, here we go. Then this is the data that is given. You have a compound that has 40 grams of carbon, 6.7 grams of hydrogen, 53.3 grams of oxygen. You know that from the periodic table that carbon is around 12, hydrogen is around 1, and oxygen is around 16. So what you do? Well, the following step is to convert grams into mole. How? Dividing by the atomic mass that is in the periodic table. Then carbon, that is 40 grams, divided by 12, that is the atomic mass, give you 3.33 moles. Hydrogen, the mass is 6.7 and the atomic mass is only 1, then it's 6.7 mole. Oxygen, you have 53.3 grams and the atomic mass is 16, then you have 3.33. Oh, look at this. As you can see here, this number and this number are the smallest. Then you choose any one of them and then you divide all the results by the smallest one. Suppose that is this one. Okay, let me tell you what to do in the following step. Then you divide all the values that you got from the moles calculation by the smallest number of moles that you got in this calculation. Then you come here and you say, well, carbon was 3.33, you divide by this, that is the smallest. Hydrogen 6.7, you divide by the smallest, that is 3.33. And oxygen, you divide also by the smallest, that is the same number. And then you get the ratios. And what represents these ratios? These ratios represent the subscripts in the empirical formula. So your empirical formula will be 1 atom of carbon per 2 of hydrogen per 1 of oxygen. Then the empirical formula is CH2O. This is a very important problem. I want you to pay close attention to this exercise. I'm going to repeat the procedure again because of the importance. What is given? the mass of the different elements that are in a compound. Sometimes they don't give you this in form of grams. They say that carbon is 40%. And then you consider that percent is 40 grams in a compound that contains 100 grams. Then you convert percent into grams. But it's the same thing that you have here already. After that, what you're supposed to do? Well, you take into account the atomic masses of each of the elements, and then you divide the mass that is given by the atomic mass in the periodic table, and you get the moles of each element in the compound. And then you choose the smallest. In this case, the smallest is the same one for oxygen that for carbon. Sometimes it's only one, the smallest. And then what you have to do, divide all the results by the smallest. And you get what? Ratios. And these ratios are the coefficients in the empirical formula. Remember that you don't write the one here, never. But you know that there is 1 atom of carbon per 2 of hydrogen per 1 of oxygen. And this is the empirical formula. Okay, I think that now our lecture is complete. And see you later. If you have any question, don't hesitate and ask me. Stop the video, watch it again until you understand the procedure.